So now I'd like to talk about heights in vertical datums because they're parallel to but modified in concert with the horizontal datums. So vertical datums are a standard surface against which we measure heights above or below a standard surface. We measure them relative to a geoid. It's a gravitational surface, and it's not the same thing as mean sea level. It's kind of our best approximation of what a mean sea level would be if it were not affected by all the other factors that change sea heights, like differences in salinity or differences in temperature or standing currents that cause the sea level to not be a very good standard surface. The other thing is that we can measure these geoid heights away from the sea very easily using modern technology. So vertical datums have changed through time. They've evolved just like our horizontal datums. Luckily, though, the vertical datums don't vary as much up till the current one as the horizontal datums have. So the distances in changing from one datum to another aren't as much as they are in the vertical dimension as in the horizontal dimension. If we're really interested in water heights near the ocean, we do measurements relative to local long-term tidal gauges. So the height surface that we use for heights everywhere else doesn't give us a sea level height near the ocean, and we have to adjust or realize that. Hopefully it will become clear after this lecture why that counterintuitive thing happens. Our lat longs are measured on an ellipsoid, right? So we have this mathematical surface that we've defined that best represents the shape of the Earth, theoretical shape of the Earth that's mathematically well behaved. The true Earth, though, undulates above and below that surface, and that true Earth standard we call the geoid. Now, a geoid is a chosen pull of gravity or level of gravity that matches, in an average sense, sea level height or what sea level height would be. So we try and pick a geoid that spends as much time over the sea level as below the sea level, because the sea doesn't follow this geoidal height. Again, because of differences in salinity, for example, where you get large inputs of fresh water, the sea water is less dense, and because it's less dense, then the pull of gravity is less strong, and it bulges up where you have fresh water in the ocean, fresher water than salt water until it gets mixed. Same thing when you have constant currents or winds. They tend to push for long terms over years to decades and pile up water in portions of the ocean. So this geoid doesn't fit the ocean surface at every location, but on average, the geoid is as much below as it is above, as best as we can estimate what the long-term sea level heights are. So it undulates. We measure our heights relative to this geoid, not to the ellipsoid. The ellipsoid is a mathematical surface, and with GPS, we can tell where we are relative to the ellipsoid, our height above the ellipsoid. But we have to measure this other thing, this geoidal height, the average measure of the distance at a particular spot between the ellipsoid and this geoid, this gravitational surface that best fits a mean sea level across the globe. So there's three heights we have to worry about: this ellipsoidal height, which we can measure with GPS very easily, this orthometric height, which is what we want to use as our standard height, and then this geoidal height. Now you might say, why don't we just use this ellipsoidal height? Well, because it doesn't undulate with the surface like we would like, and locally water will flow downhill on these orthometric heights and not on these ellipsoidal heights. So we want to have something that is consistent as we can with our previous idea about heights, and that's this orthometric height. It's height above a level surface. So our real task in fitting a vertical datum is to try and measure these geoidal heights, and so we can calculate these orthometric heights all around the globe. And that's why we've updated our vertical reference frames, or vertical datums, because we've gotten better and better, more dense and more accurate measurements of these geoidal heights. We can then model them across the landscape. In any place we have a GPS measurement that gives us the ellipsoidal height. We can calculate the geoidal height and then get our orthometric height. That's how we typically do it. Right? Horizontal and vertical datums are linked. When we're doing our horizontal survey and we have these well-known points, we know the location, their latitude and longitude, so it's only natural that we use a subset of those points to measure our heights, to measure the ellipsoidal height, the geoidal height, and hence the orthometric height. So as we've improved the network of horizontal measurements, we also improved our network of vertical measurements and do a comparable analysis to get better estimates of heights. Right? These geoids are an imaginary surface at a given gravitational potential. Right? So we have a reference ellipsoid. What we're doing is saying, what's the pull of gravity, what's the height of the pull of gravity for a standard pull of gravity relative to our ellipsoid. So we measure gravity above the surface and infer down to where that standard pull of gravity is. And we have measurements all around the globe, so we can measure kind of the difference in the strength of the pull of gravity and get this surface that's a constant pull of gravity. So these are the height deviations from our ellipsoid, shown here in colors, of this standard surface, the pull of gravity. So it's bulging up high here. These red colors mean that our standard pull of gravity is much higher in a portion of the globe, or where it's a dark blue here, they're bulging down lower. They're basically settling. So that means the pull of gravity is lower relative to the ellipsoid at our standard equipotential. So we're just saying, well, if we had a perfectly still ocean with no wind and no pull of the moon and no differences in salinity and no differences in all the other factors that can affect the height of the ocean, this is the surface it would take across the globe. And because of differences in density below, that gets pulled down, that surface gets pulled down or comes up above. In the olden days, we, again, didn't have this model of there being a variation in that gravitational surface. We thought that sea level along the coast we could measure, and if we measure inland from the coast, carefully measuring heights, we could meet in the middle, and the heights would be the same at some point in a mountain in the middle of the continent. It ends up not working out that way, but for the longest time, maybe up until the 1960s, 70s, we had that view in mind. We were going to measure these locations carefully and then establish a benchmark, and we might have to remeasure them if there was tectonic uplift, the plates were pushed up or down because of an earthquake, a sort of shift up and down, but that we wouldn't have to worry about remeasuring locations because of changes in the gravitational pull that we thought we would just have to measure better. We had instruments that were optical instruments, and to level, we would have to measure across the landscape, measuring angles and distances to get differences in height. So it was laborious to get a measurement in Colorado because we weren't close to any ocean. Today we use GPS. We can get accurate three-dimensional locations down to sub-inch in a few hours and down to a couple inches in a few minutes. So we can use this GPS to give us our 3D point location, and that's relative to the ellipsoid. So we had to come up with a system which took advantage of that to get that height, to measure relative heights. And so that's why we changed to say, look, we're going to use an equipotential surface. If we measure where that equipotential surface is everywhere, and we can get that geoidal height, get this estimated everywhere, and get this from GPS, then we can calculate our height really quickly. So our current or modern datums, or estimated vertical datums, are focused on estimating these geoidal heights, right? Again, in the old days, we used to start at the ocean and measure heights, changes in heights over distance, and accumulate those. And for key points, mountaintops, the top of church spires, other things, we'd do this leveling and calculate heights and then monument those heights. And we had a big network. And the idea was we'd start at standard gauges where we had long-term measurements, and we would measure inland and get heights of things relative to these sea levels, with the idea being that the sea level is going to be the same height all around the coast. But it ends up not working out that as we level into the center, we measure through these leveling surveys that we analyze all the data together, consistent heights in the middle. So this orthometric height they identified as a height that's always at right angles to all the equipotential surfaces from our base surface to the height of interest, in this case our ground height. Now these undulate somewhat, and so this line that's always at right angles actually isn't a straight line. Most places it's pretty close to the straight line. It might arc or bend a little bit. And functionally, the distance on a straight line or along this curved path isn't going to be different. But if you read the documentation, the definition, it'll say that it's a distance at a right angle to every intervening equipotential surface from our base value to our point of interest. Right? So again, we're measuring along these. Now there's lots of equipotential surfaces we could use where the pull of gravity you consider constant. And we actually don't have to use this pull of gravity as a constant as our base surface. Some countries don't. Australia doesn't, for example. Across their continent, they have the same thing. They have basically tidal gauges on one end versus another that are different. And they split the difference. They basically say we're going to fit a surface that kind of averages across those. So their base cuts across these equipotential surfaces to average match tide gauges around the perimeter of the country. There's no reason we have to choose this. We've just chosen this for a number of reasons and ease in measurement and analysis. So these surveys that went all the way across the country from 1927, we used that set of gauges along the edge to 1983 with the 1986 datum. They did an analysis to try and match basically the heights across this network, starting at gauges at both sides. These are more precise measurements than the old 1927 or 1929 vertical datum. And so they were going to do a 1989 or 90 vertical datum in concert with this 1986 horizontal datum that we talked about earlier. The problem is they found that there were discrepancies across the continent that they just couldn't resolve to measurement error. So we had a 102 centimeter difference in height relative to a standard and a minus 23 centimeters. So this is almost 3 feet, and this is about a foot, a little less than a foot, 10 inches, below a standard surface. So if you measured across in the middle, a point in the middle, coming from this direction as coming from this direction, you'd have more than a 3 foot difference in height, about a 4 foot difference. If carefully measured, carefully analyzed, it was inconsistent. So that's when they decided we're not going to, in the new datum, try and assume this idea of there being mean sea level at the gauges, but rather fit a surface on a global level, this equipotential surface, and try and pick one that sort of averages the errors or the differences, the discrepancies, because they're not really errors, across the globe of sea level height and this ellipsoidal height. So you have this geoid that goes up and down. Because I could pick any one of these as my standard. I just picked the one that spends as much time below the ellipsoid as above the ellipsoid, so that it minimizes the deviation from the ellipsoid and the size of these geoidal heights that I'm trying to calculate. So they decided to fix the reference frame to one sea level station and just calculate heights relative to measurements at that station. Right, so there's a bunch of versions of this, just like the horizontal datum when they were working in 83, 86. They realized, that this GPS really helps, so we're going to use the geoid that we estimated and the geoidal heights that we estimated with these, and we'll call it the NAVD 88, and continue along. I'm sorry, this is a mistake. This should be NAVD 88 also. So what they're doing basically is along the level here, coming out with the NAVD 88 Geoid 3 and using it for the first Harn in 1996, and then by 2007, 8, 9, estimating a new geoid with the new measurements, and then again in 2011. So they're sort of following behind, delaying the vertical adjustments as they gathered more vertical measurements based on where the locations were calculated for the horizontal adjustments. So we have a pre-1980s geoid, the NGVD 29, or height reference. And then we use several geoids, the 2003, 2009, and 2012. And these geoids are different estimates of where that standard surface lies. And so we're saying we have various versions of this surface. We're trying to estimate it, but as we get more measurements, the surface changes a little bit, and that changes these geoidal heights, which changes our orthometric height. So each of the geoids gives us a different one. Why did it change? Well, because we use a physical instrument, a gravimeter that we tow across or drive across the surface and then take measurements at locations, or put in a plane and take measurements at locations, or a couple of satellite systems. So the GRACE is a study where they have two satellites flying in concert. As the pull of gravity gets stronger, one satellite gets pulled closer, and because it has a smaller radius, it speeds up, and the distance between it and the trailing satellite increase. And then as the second satellite gets in, it speeds up and catches up, and then where it gets weaker gravity, the first satellite rises and slows down, and the distance gets even closer until the second satellite rises, then it spreads back out. And so by measuring the distance between these satellites very carefully, right directly below the orbital path, you get a large area aggregate estimate of the average pull gravity. And it says that spins around the globe as the globe turns. You can pretty much cover the whole globe and get a large scale estimate of the variation in the pull of gravity. There was a similar single satellite measurement that the GOSI, I think, that the European Union set up, that used a single satellite and measured the height of the satellite constantly as it undulated up and down with the strength of the pull of gravity. That plus the ground measurements, the gravimeters, gave us an increasing, improved density of measurements. Now you can see there's some statewide contributions. So North Carolina and Wisconsin and Minnesota and Florida are known for having very active geodetic state-level offices, and so they have a real high density of these ground-level measurements. Other states, not so much, and so there's still room for improvement. But nonetheless, we have measurements of these geoidal heights at all these locations, and so we can develop a model that allows us to calculate orthometric heights at all these locations. The previous 2009, this wouldn't have been as dense a network, and the 2003, even much less a dense network of measurements. So you have to use these datums, horizontal and vertical datums together, right? So the NAVD 88 was with the Geoid 3, and the NAVD 83 was with the Geoid 3, and NAVD 88 Geoid 9. This is with this NSRS 2007, the 2000 version of the vertical datum. The NAD 83 2011. Now this realization that they're paired is important, particularly with LiDAR now, because people are developing and generating a bunch of LiDAR data measured relative to a specific geoid. And you can calculate an offset in a location, but if you use a different geoid, but you have to know which geoid the data are delivered in. A lot of the data are getting delivered in a European geoid and WGS ITRF related geoid, the CGMS geoid. And so the height reference is off by about a meter from our NEVD88 geoid. And just like with the horizontal systems, we have software we can use to calculate the difference in height due to a different vertical datum. We have to go and do that if we get data in a different datum. So the main point here is that these geoids have changed through time. Our vertical height references change through time. And you have to pay attention if you want to know precisely what the height is, how these have changed through time. So you got to use the right one and use the right tool to calculate an offset. And the good thing is, regionally, they don't change very much. So if you know the offset between the Geoid 12b and the Geoid 9 in southern Minnesota, the one number is generally good for much of southern Minnesota. So the offset varies some. You should always use an offset for your study area, but you don't always have to calculate this difference for every point in your study area for heights. So basically we have these different geoids, different undulations. So we'll have different geoidal heights. How much do they change? Well, from the latest one, this 2012b, to the 2009 one, it's only 1.7 centimeters, less than an inch. To the 2003, it's about 3 inches. To the 99, and this is at a point here in southern Minnesota, south central, it's again about 2 inches, and the same thing for the 96. So the geoids are varying in that sort of 1 to 3, 1 to 4 inch category, and that's not a big difference for a lot of applications, but you still should get it right. Now the difference to the WGS84 ITRF is bigger. If you get data, horizontal data delivered to you in this WGS84 ITRF, it's probably also using the worldwide or European datum, the EGMS, and so you probably have about a meter difference. And that's the biggest mistake folks make, is they're getting a geoidal height, but with a different underlying ellipsoid, so there's a big difference in the geoidal height. And in Minnesota, it's, I don't know, 60 or 70 centimeters between the WGS84 ITRF version and the NED83. And so you have to understand what is your vertical reference and go to the software to calculate your offset for your area. Now, the software is available at the NGS, just like that HTTP software is. There's a VertCon for a vertical conversion, right? Height changed substantially between ND83 and ITRF. I want to reiterate that. So you have to be really careful, right? Here, at this particular point, it's about 0.92 meters. It's probably a good average for much of the U.S. In some places, it's 1.5 meters. In some places, it's like 20 centimeters. So this geoidal 12B height, which we want to use, we're using NED83, is going to be very different relative to the ITRF and the NED83. So, that's the biggest mistake that folks make. All right, so I showed earlier this notion of there being many sea levels across the coasts, and we don't use sea level as our base. We use sort of this main undulating equipotential surface. But that means that the equipotential surface at the coast, the zero line for our equipotential surface at the coast, isn't at sea level, mean sea level at the coast. This is what the difference is, 1 meter, 70 centimeters, or minus 23 centimeters. So there's a big difference in where our zero is and where the mean sea level is at the coast. It's kind of odd, but you actually have an average height of water relative to our base standard at almost every point on our coast that is different than zero. So the water is at 1.25 meters, or about 4 feet. Well, mean sea level is at 4 feet of height up near Seattle here. There isn't the same thing. So if you want to look at heights near the ocean and you want to look at how far above or below sea level, if something's going to get inundated or not, then you have to look at a local tide gauge that's been measuring for a long period of time and look where our standard height is relative to the sea level height. And so there's a NOAA website that gives you sea level heights, and they have a local datum. So they have a 0 for sea level height, and they have a mean sea level height that's 4.05 feet above that datum, right? So they, 6.73 feet MSL. So that's the mean sea level above that local datum, right? So, and our NAVD height is at 4.22. So we have basically a mean sea level height that's 6.7 feet in the NAVD, which is 4.22. So there's about a 2.5 foot difference here between what we have as our NAVD level and our MSL level. So there's a 2.5 foot offset there. That means really we want to use this mean sea level. And if we have a height here in our NAVD reference, we have to subtract that 2.5 feet because it's not 2.5 feet above sea level. All right, it's 2.5 feet less above sea level. Let me try and be clear about that. We have to subtract that 2.5 feet because let's say we're 10 feet above our NAVD 88 reference. Well, we're less than 10 feet above mean sea level because there's 2.5 feet extra here. So it's about 10 minus 2.5, or about 7.5 feet above mean sea level, above the local sea level. We have to look at this difference between the mean sea level and our NAVD 88 heights to figure out how far we are above the sea level at the time, right? So again, 2.51 feet is the offset. Now, the good thing is it varies in gauges across the coast, but it doesn't vary much, and you're never very far from a gauge. So the offset is 2.51 at the point I picked, and it's 2.6 a little further up the coast, and 2.62 and 2.6. So you can use a number to calculate your local offset across a pretty broad region or stretch of coast, and it's the same most everywhere. And so I can do that calculation. For a different gauge, I'm going to get a different value, right? So this is a different gauge. The mean sea level is 6.11 above its local datum, and the NAVD 88 is 3.5 above the local datum. So it's 6.1 minus 3.5. So that gives us the offset, right, in that particular location. So we always have to go and look at these various offsets and use them in our calculations. Okay, again, to reiterate our main points, we have two primary types of coordinate systems, the spherical geographic and 2D Cartesian projective. For the spherical cartographic, we have a datum that's an ellipsoid, a mathematical surface, and a well-measured set of points that goes with it. These datums have improved or changed through time in the past 3 decades. This can cause confusion in the GIS. You always want to use the latest version if you can. You want to convert data to this 2011 version of the horizontal points. But whatever your data are in, you can use a datum transformation to get them back or forth into the same datum. You don't want to mix and match datums in data that you're going to combine in an analysis because things won't fall in the same place. The coordinates change because we've gotten better estimates of where our key points are. We have to make sure we don't do it incorrectly. We measure vertical heights with reference to a geoid defined by gravity, and these have improved and evolved through time also, but the versions aren't as different within the NAD83 family. The difference between the WGS84 ITRF, the worldwide system, and the US specific system are greater. And so those datums, vertical datums, we can't mix and match in analysis. We have to convert to the same one. Now, if you look at the horizontal shifts through time, this figure is key. It shows you that we've got these datum shifts as we've improved our measurements here in the US in this NAD83 family, from the original NAD83 1986 down to this CORS 2011. There was a big shift as we went from the early estimates to these later estimates, a meter and a half. The later estimates here changed by an inch or so. 2-3 centimeters. So these really can be considered equivalent for many analysis. These are off by a few feet. The WGS and the ITRF-84 are kind of the same thing since the mid-90s. They've been adjusted to coincide, and they're better estimates. The same thing, there's 10 centimeter, 2 centimeter, 1 centimeter. Things here shift only due to minor differences in the improvements in technology, because they didn't start till later on, right? They skipped the mess that we had because they started later after we had satellite technologies. That's where the push was to put these together. And the changes here mostly due to plate tectonic motion in any one location. So if we want to convert between the worldwide system and our system, we have to use a datum transformation, because those differences are large, up to 2 meters. Over most of the US, it's around 1 meter, 3 feet. And so if we have data in one system, like GPS, we have to convert it correctly into our other system. And we can do that because whenever we come out with a new datum, we typically calculate, we being the engineers that do this, the geodesists, the transformation back to the most current datum in your family, and the transformation across to the other complementary datum. So when they came out with the ITRF 2008, they said, here's how you go from 2005 coordinates to 2008 coordinates in the ITRF system. But they also said, here's how you go from the ITRF 2008 to the NAD 83 cores 96. So they gave equations for that. So if we want, we can go back or down this chain to anyone and then across through a datum transformation. Sometimes we have to play multiple datum transformations, right? Remember, we're using an orthometric height, which is a height above a geoid. We get this height through measurements using gravimeters, right? Relative to this geoid, we can measure the geoid height and calculate the ellipsoid height at any point, and then get a model of this geoid. From GPS, we can get this ellipsoidal height. If we know this and this, we can calculate this very easily. So using a GPS out in the field and this model of the geoidal height, we can calculate our orthometric height. And that's how we do it these days. Remember, there have been various geoids. The ones that we use in the NAD83 or with the NAD83 system have varied a little bit, 1 to 3 inches, as they've improved across the country for most parts of the country. The European geoidal heights differ a lot from ours, but that's because the ellipsoids are different, right? So their ellipsoid doesn't correspond with our ellipsoid. It's about 1 meter off. And so heights in the European system would be different than heights in our system. So if somebody gives us something relative to the European ellipsoid, we have to convert that to our vertical datum before we calculate a height.